have the upper half plane, which was complex numbers with strictly positive imaginary part. And there's a measure on the upper half plane that comes up a lot. It's very convenient, dx dy over y squared. And the point of this measure is that this is invariant under Mobius transformations, under z maps to az plus b over cz plus d, right? This was the action of SL2z or PSL2z on the upper half plane. What this means, saying this is invariant, is that if you have an integral on the upper half plane of some function f of z dx dy over y squared, that's going to be equal to the integral, still on the upper half plane, of f of gamma z. And then here you can write the same thing, dx dy over y squared. So what we're doing is we're doing a change of variables here, but the measure doesn't change. In this way, it's similar to the fact that dx over x is invariant under x goes to ax, which is maybe a familiar fact when integrating over the real numbers. So this is going to be useful. The reason why this is true essentially is because the imaginary part of gamma z is equal to the imaginary part of z divided by the absolute value of cz plus d squared, where here gamma is ABCD. And this fact is going to be useful on its own quite often, so it's good to keep this in mind. So this upper half plane is a model of the hyperbolic plane. So this is called the Poincaré upper half plane model. And maybe you're familiar with other models of the hyperbolic plane. So one other common one is when you have a circle, and for example, this comes up in the art of M.C. Escher, and the geodesics, the straight lines, are sort of these curved things, sort of looking like this. You can look up some cool pictures from Escher and get a better idea, right? So this is and this is called the disk model. The Poincaré upper half plane model is really due to this Italian mathematician Beltrami. And the edge of the hyperbolic plane in this model, in the same way that when you get sort of close to the boundary of the circle of the disk here, then weird stuff might start happening. Here, the boundary is the real axis, and the geodesics are semicircles that intersect or that touch the real axis at right angles. So these are all geodesics. And you also have some geodesics that go just straight up and down. But the key thing is that they all intersect at right angles. And as you get really close to the axis, you got to be careful. This is this is considered, like a lot of a lot of distance essentially in hyperbolic space, and you can sort of see this in the measure where when you're dividing by y squared, that means that down here some funky stuff is happening. And then you also have one point at infinity that's also sort of the edge of the hyperbolic plane. So it's, the edge is going to be the real axis and this point to infinity. And the geodesics, they look like semicircles. And this metric also, I should say, is called the Poincare metric.